Alright, everyone, June the 1st. Very unfortunate that I still don't know how to do this. I think I have to go with a hint. Very disappointing, because like I said, I definitely done something similar in the past. I just don't remember. Or I just got stuck somewhere. Lordy. You're given a list of bombs. The range of a bomb is defined as the area where its effect can be felt. This area is in the shape of a circle, with the center as the location of the bomb. The bombs are represented by a zero-index 2D integer array bombs, where bombs I, xi, yi is the center, and ri is the radius. You may choose to detonate a single bomb. When a bomb is detonated, it will detonate all bombs that lie in its range. These bombs will further detonate the bombs that lie in their range. Given a list of bombs, return the maximum number of bombs that can be detonated if you are allowed to detonate only one bomb. This is the type of question that's very, very good, fun, and I think it'll be very interesting too. Lordy, I have 5. Detonate this. The 1 go, 2 goes. What do you think? 100. What do I think? It's basically a range, right? But it's slightly different. We might have to reorder them in terms of their... Reorder them how? Reorder them in terms of the distance between their centers, right? Because that determines whether it can be detonated or not. So we will find the bomb that's mostly but it's a 2D system. But hey, it's 100. I may be able just to brute force it. Right? I mean, think about it. Everybody is larger than 0, right? Yeah, everything is larger than 0. So we have a system, and then we have, doesn't matter, these bombs. Now we pick a bomb and detonate it, right? It has its radius. And we will find all the distance between it to everybody else. Can we do that? Yes, we can. Yes, we can. We can find, basically, and so we say like bomb 0. So it's gonna be like a matrix, okay? Right? Let's say we have 4 bombs. Bomb 0, 1, 2, 3. Its distance to 0, 1, 2, 3, right? The distance to themselves is 0, but distance to 1, distance to 2, distance to 3, right? 1, distance to 2, distance to 3. So we will have this matrix, and then what do we say is if it detonated 1, we want to know who is in range. I know the radius, right? Then I need to know within this who is in range. Okay. So if it detonates 0, let's say I can do these detonated. And then I want to know if detonate 1, who gets detonated. And detonate 2, who gets detonated. Detonate 3, who gets detonated. So for every single row, I can know. So I have, let's say we have a Yeah, basically, no, we don't even need to record. All we need to do is, let's say we have another matrix, okay? It's not distance. It's who will get detonated. Maybe a matrix is not necessary. Maybe we can just do a dictionary. Not really a dictionary, a sparse matrix, right? So 0, I say, if 0 detonated, we can cause, let's say, 1 and 3 to detonate. And then for 1 detonated, we go through everything, and then we say we'll cause, I don't know, maybe 3 to detonate it. Okay? And 2 detonated, we have nothing. And 3 detonated, we have, let's say, 0 and 1. Right? We have something like this. Then you build this. This is like a graph, right? This is a graph. This is a graph, right? 0, you connect to 1 and connect to 3. 0, then I can do this, right? 1, you can connect to 3. And then 2 is just by itself. 3 connects to 0 and 1. Okay, you have a graph. Then the question is, start from where? So what's the longest path? Right? That's the question. What's the longest path? So you just DFS to find the longest path. Okay, you DFS to find the longest path. Yeah, because everything you visited once. Right? So you start from one node, and then you say, okay, I want to find. I just keep going, keep going, keep going. Until we cannot go anymore. Either it looped back. So we have a visited. Yeah. And then we can backtrack. And then we go down the other path. And backtrack nothing, we backtrack. Done. Yeah, we can backtrack to find the longest path. The longest number of nodes. Let's try this. So first things first, we need to build a graph. Okay, so we need a graph. Right, how do we do the graph? Well, for bombs, we need to see for it's a directed graph. It's not even a, so yeah, it's a directed graph. For I in range okay, and we say and we can do this for I x y x1 y1 r1 in enumerate bombs. For j x2 y2 r2 in enumerate bombs. Okay. Well, detonate I, what do you say if j can be detonated, right? So we say the distance is equal to if I is not equal to j, and distance is equal to x2 minus x1 squared plus, well, it's dist squared. This is squared, right? And then y2 minus y1 And then we say if r1 squared is larger or equal to distance squared, which we can basically just do it this way. We don't have to. We can do this, right? Detonate I, and r1 is radius, and so it's larger than the distance. And that means we say graph I dot append j. Otherwise, we go through everything. Now we have the graph. And then we say DFS will do the maximum, right? Well, we need to do the maximum. How do you do the maximum? So basically, we start from anything, and we go through them. Yeah, we shall say the maximum. How do we tell this? So we have a graph, right? We want to know. What do we want to know? We want to know the size of the maximum connected graph, right? We want to know the size of the maximum connected graph. How do we do that? So we start from one node. We want to see, okay, the maximum size of everything connected to this, and then I DFS. So I say the maximum on the left tree and the maximum on any of those, right? We want to find the maximum. And once we're done, yeah, I think we can do this DFS, right? So DFS give us the maximum. We have the node, and we don't return anything. Do we return anything? We do, right? We do. And we also need to have visited. We might as well just do visited here. Visited equals the set, right? Okay, node. So when we hit the node, we want to know the maximum graph containing this node. So res equal to 1 because the node, right? And then we shall say for neighbor in graph node, if neighbor is not in visited, oh, I need to visit as well. Visited.add node, right? If neighbor is not in visited, then we need to DFS the neighbor, and this will give me the largest that the neighbor has done. And then we can say res plus equal to this. It's the total number of nodes in the neighbor network, right? And when it's done, and if the neighbor is in it, then we don't do. So blah, 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 then we will return res. Okay. Then what we're gonna do is for node in range n, okay? If node not in visited, I'm gonna have the res here equals to 0. Okay, res equal to 0. And the res equals the maximum res and DFS node. Right, and now we return res. Yeah, let's call this num nodes. Okay, let's give this a shot. That's quite fun. Okay, this is gonna be bombs. All right, this is gonna be right. Unfortunately, the first one's not right. Okay, let's take a look. at the graph. Graph 1 to 0. So we go 0, 0 not in visited. Then we do DFS 0. Okay, and then return 1. Then DFS, oh shoot, it's visited. Damn it. Damn it. All right, so basically we cannot do it here. Visited. We'll do it here. Visited.add and visited. So every time we go, we'll say a set. So this basically means every single time we will visit the entire thing. Okay, that's fine. That is fine because it's only 100. So this is O(n) squared, right? Because you think every time you DFS, you'll go through the entire thing, right? It will go through the entire thing. But it's still, you know, if we can, but we cannot because it's a directed graph, right? So you have to try every single one. Okay, O(n) squared. Let's try this. Do you have any edge case you want to try? Nah, it's too complicated to figure. I mean, we can. Let's say just this. 1. Because the length is 1. Right? Yeah. Alright, we'll give this a shot. Not bad. Not bad. But it's a very fun problem. Very, very fun problem. We can convert the bomb detonation relationship to a directed graph. Then the problem is converted to finding the size of the largest connected graph. Converting the bombs to graph takes O(n) squared. Finding the largest connected graph also takes O(n) squared. Okay, let's go to the solutions. We return the size of visited as the number of. That's, yep. Build a bomb. Yeah. This return visited. Oh, that's almost exactly the same. O(n) to the 3. I say O(n) squared. I was wrong. Wait a minute. This is O(n) squared. O(n) here. Oh, yeah, because we have this, the DFS. But hold a second. The DFS But the DFS only goes through every node once. Why is Owen... Oh, it's the number of edges. You don't just go through every node, you also go through every edges. That is true. There could be many edges. For each node, we may need to explore up to n-1 edges. Owen squared. Yep, I was wrong. This is right. This is Owen to the triple because the number of edges is to the order of Owen squared. Because each node can be connected to every other node. That is correct. You can BFS this. Yeah, I guess you can. Yeah, it's the same idea. Anyway, good problem, right? Good problem. All right, let's go back. Let's peek at a hint. How can BFS be used? Okay. That was a good hint. Did not reveal anything, just say, think about BFS, right? You would always think about DFS. Think about BFS. I think I thought about BFS yesterday, but didn't really get anything out of it. Do I have a good? I know I have. Oh shoot! I have a time limit. What's this one? This is a good one. Let's try this. Which one is this one? This one is this. Okay, let's try this one. 0. Oh, I remember. 1, 2, 3, 4, 5. 7, 6, 5, and 5 to 6. Yep. Yeah, that's the one I got wrong yesterday. So you asked me to think about, maybe I should think about an easier case. Let's just say 0, 1, 2. How'd you BFS this? Oh, you start with a node. Okay, so we start with 0. And next you go to 1 and 2. Okay, because that's left and right. And then from 1, you need to go to 0 and 2. But 0 is visited, so you can now go to 0. 2, usually the way I do BFS is also visited, so you can now go to 2. Yes, the problem I have with BFS is how do you tell the difference between this and this? What if we let's say let's say the first queue we have 0, right? And the second queue we have 1 and 2, neither are visited. And at 1, I don't visit anything, so on 1, to the next level on 1 I visit 2. Okay, and at 2, because 0 visited, I visited 1. But hold on 1, 1 is already visited, right? Because when 1 comes out, I'll visit 1, which means I put 1 into the visited set. And 2 hasn't now visited yet, so I put 2. But now I go to 2, 1 is visited, so the end is going to be 2. Okay? The end will be 2. Now the last one, 2 comes out, and I see that 2 has already visited, but I still put a 2 here. So that means we have a cycle, right? That means we have a cycle. Okay, but how do we decide the size of the whole thing? Oh, visited, right? The size of visited. That is not true. That is not true. But at least we know 2 is inside a cycle. So we can start from 2 and maybe do BFS, do DFS again. But if you're here, how do you do DFS? You still go 0. I can say a 0 go 1. And then you can say from 0 you go to the second. And you will go back here, but you also go back here, and you can do 6. So you only do 0, right? Because you know 0 is, so here we just do 2, and then we go back. Maybe. Maybe. Because if it's a cycle, I don't think we talk about this, right? If it's a cycle, eventually you will converge. Let's try another one. This is 3, right? Let's try 4. Let's try this. 3, 4, 5, 6. Okay. So we start, it doesn't matter, we start with 3. Next we have 4 and 6. Next we go 4. 3 visitors, so 4 will have 5. Okay. And 6 will have 5. Okay, that's fine. Next 5 come out. 5 come out. We visited. At this point hasn't visited yet. So 5 come out, we visited. And then 4 and 6 visit, so there's cannot go, so doesn't go anything. Now the second 5 come out. It sees that the 5 already visited, so we know 5 must be in a cycle. So we seize it. So say we're gonna do starting from 5. Okay, I'm from 5, and now we do a DFS. But is it possible that we figure out the size just by doing, actually I'm not sure. Okay, so we kind of play around with these two baby cases. Let's now try this more comprehensive case. We'll stop on 0, okay? The first level is 0. Second level, we have 1, 7, 6. Third level, 1 will go 2, 7 will go 5, 6 will go 5, right? Next level, 2 will go 3, 5 will go 4. But this 5, oopsie doozy, we got it, right? So this 5 already, we hit it, Okay, we already hit it. So we say, oop, 5 is going to be, so we actually cancel this because the first time we hit, that means it's very short. But the exact size, do we know the exact size? I guess we actually do. Well, if you think about it, because from anything, right? If you have two levels, you go down, right? That got to be 4. Now, if you converge, right, 2 levels go down, it got to be 4. I mean, if you have like multiple, that's what I'm thinking. But still, you got 1 level and then 2 level, right? That doesn't really matter. If you got 2 level, you converge, that got to be 4. You have a converge case. And if you have more levels, so 1 level, 2 levels, then you converge, right? Because at the end of the day, it's just gonna be, because it's a loop, right? It doesn't really matter what the loop is. You can have as complex a loop as you want. You always start from 1, right? And you go 1 level. They always go to the next level, always go to the next level, and then they converge, right? And each level is 2, right? So there's level 0, level 1, 0, 1, 2, 3, right? And then we converge. So it will be 8, right? That will be 8. So now the question is, what is the case of this? Odd number circles. Well, odd number is slightly different because odd number, we go 1, then we end. Huh. What is this? This is 1 level, 2 level. 2 times 2. 1 level, 1 times 2 plus 1. If it's even, that's just 2 times 2. Let's try 5. 1, 2, 3, 4, 5. Okay, so I have 1 level and 1 level, 2 level. 1 level, 2 level. Oh no, it depends on how you get it, right? Because in here, when you get it is at the end, which means you're doing one of them, okay? You're visiting this, and then you're doing this, and you find out that, so you're visiting this, you push this in, and now you're doing this, and wait, hold on. How do we do? One more time. So you're doing 0, right? And then you have 1 and 2. Okay. Then 1 out, you visit 1, and you push 2. Right? So 1 out, you visit 1, you push 2. Now 2 out, and you'll find that 2 is already been done. What's the difference between this and this? Huh. Yep, I think that's the question. What's the difference between these two cases? Well, the difference is if we have if the difference is this we push it and this we push it, that we have a duplicate when we push. This is when we analyze, the duplicate happens like on the top. That's the difference, right? This duplicate, if we have 1, right? And then we visit 1, then we push to we find 2. 2 has not been visited yet, so we'll push 2 into it. And then we go for 2, and 2 want to go 1, but 1's visited already, and 2 finds that it's already in the next queue. If it's already in the next queue, right? If the previous level, it finds that it's already in the next queue, then that is this situation. If the previous level is not in the next queue, but the one you want to push is in the next queue, that's in this situation. So I can start from 1, visit every single body, right? And then come out the first time that we hit. And then what? And then we need to keep going, right? We need to keep going. Keep going. Starting from a different one? Yeah, how do you know that whatever you did is the best? You don't. But the ones you visited already, they are not gonna top. So you can keep the visited, and when you find another one, you just using the same visited. Okay, let's give it a shot. We'll need this one for sure. We'll have visited for sure. We'll have res inf for sure. And then we'll have a BFS. Okay. Let's try a BFS. BFS, we're gonna start with a node and what do we return? We can return an int, the smallest that we can find. Okay. So what do? We have a queue, but a queue will be a set. Okay. And while queue, and the temp is going to be a set. Okay. For node, and let's call it root. And say for node in queue, we visit it here. Okay, we say visit.add node. Okay, for neighbor in graph node. Oh, we also need to know levels. So we start from 0. Okay, so for neighbor, right? If neighbor is in temp, is already in, okay, then that's the case of the odd number. Okay, then how do we know the number of levels? Well, when you know that's you have to go to this level. We have to go to the final level, right? So if it's 0, final level is 1, right? Final level is 1. So the level shall already be good, right? Then we shall return right here. What do we return? Well, we have the current level, and that's going to be 2 times level plus 1. neighbor it's in temp, well, we might as well visit it as well. Dot add this neighbor. Okay. If neighbor in temp. Wait, hold a second. No. No. This neighbor in temp, that's the first case. That's the even number. That's the even number. That's the even number. Okay, current 0, and then plus 1, we had this level. Okay, and then we are pushing down. Okay, and then this is pushing down as well. This is pushing down as well. So the neighbor, if neighbor in, then that shall be level plus 1. This is even number of nodes in cycle. Okay. If neighbor in temp, that's done, right? And if neighbor is not in visited, then we can say temp.add neighbor, right? Well, we have the handle here for node in queue. If visitor, so we'll add node, that's fine. If node is in temp already, this is odd number of nodes in cycle. Then we shall return 2 times level plus 1. Otherwise, we can say q equals temp and level plus equal 1. If anything, we return mass.inf. Okay. Then what do we do? For I in range n, we basically say res equals to the minimum res and BFS I. Of course, if I has not been visited before, right? We say if I is not in visited, we do this, and now return res if res is smaller than mass.inf, else -1. Let's try this one. So far, so good. We need to try the one that we got timed out yesterday. This is good. Oh my god, how am I supposed to do this? I have a thought. What if we put visited inside? We put visited inside, and we go every single one. Gosh, this might time out though. Oh, it does not time out. You do have to start from every single one. Huh. Interesting. I shall work for this one as well. Yep. You wanna try? That's not encouraging at all. Oh, holy crap. We're almost there, but so close, but so far away. Expected 3. Alright, this is not too big, so we can draw it. Let's see. What the hell is wrong with this one? 7 and 3. Jesus. Okay. 3, 7, 1, 5, 0, 6. Lord. 3, 1. Okay, I'll put 0, 6 somewhere else. 3, 1. 0, 6, 6, 2, 7, 4, 3, 2, 5, 2, 6, 5, 0, 3. Oh my goodness. What the hell is this? Okay, 3, we have 7, 0, 1, and 2. Okay, 7 go to 4. 1 will go to 5. 5 will go to 2. And 2 will go to 6. And 6 go to 0. So it's like this. I'll remove this. Remove this. Let's double check. 7, 3, 1, 5, 0, 6, 3, 1, 6, 2, 7, 4, 3, 2, 5, 2, 6, 5, 6, 5. Lordy, there's a 6, 5. There's a 6 here, so 0, 6, 2, 6, 5, and 0, 3. How do we not handle this one well? I mean, we don't have to look at this. If you start from 6, or you start from 5, right? 5 will hit this, this, and this. And next round, 6 will hit 2, and 2 will hit 6. Why did I not handle this one? I need to take a look. Six, right? 6 shall do. Oh, lordy. Okay, let's do this. So 6, okay? So we start with 6. Next round is 0, 2, 5. Okay, 0, 2, 5. 0 cannot go 6, so 0 will go to 3. 2 cannot go to 6. 2 will go to 3. Oh, 2 will go to 3. So I'm recording this. Okay. Which means I shouldn't return at the moment. What I should do is have the size here, math.inf. Okay. So if this, then we say size equals minimum size, and this, and we let it go, right? If neighbor in this, we say size equals minimum size, and this, we let it go. You gotta be kidding me, man. Oh, because I should have written size. I think that might be right. Oh, sorry. Maybe. I want to take a shot. Like, seriously, I want to take a shot. If n not in visited. Oh, nah, can do it. Oh, if I not in visited. Meh, can do it. You have to try it every single one. Why? Well, because some might be visited from the other way, right? From the wrong side. You visit it, and then it's visited, and you don't do it again. Yeah, that actually makes sense. That doesn't make sense. So now I don't need this. Okay, so let's try this one. We got it. This is completely different from what I remember. Do the cycle or not cycle. So I remember doing something similar in the past, cycle or not cycle, but this is very, very different. BFS, I took the hint. I mean, this is basic BFS, right? The only difference is this and is these two. These are the only difference. Everything else is just standard BFS. Standard BFS. And the runtime. Well, what do you say about the edges? I mean, BFS, we have to go through every node. So it's n plus edges, right? N plus v, v plus e. And then we go, so the runtime, I can say, use the hint. Although, that said, the hint was as simple as can BFS be used? So the solution here uses the most generic BFS, but with two checks for even numbered cycle or odd numbered cycle. Okay, for even numbered cycle, we will put the same node in the next level. Okay, so when that happens, we can record the size of the cycle. For odd numbered cycle, we will notice that a node at the current level has been put into the next level. When that happens, right, we record the size of the cycle. One important aspect is that we do not quit BFS the moment a cycle is found because the way we code it, honestly, yeah, but the way because the way we code it cannot guarantee that the first encounter of a cycle is the smallest. See the 0, 1, 2, 3. So you see tests. I'm wondering if we start from 6, right? And this one goes this one goes this. Can we, because this one also goes this, right? This one goes this is already a hit. But honestly, we haven't got to that level yet. So then this one goes this, and then when we have this, it's already in it, so we will handle this. Can we not and like wait? Seriously, like wait. But how do you wait? Because when you hit here, right? When you hit here, the only thing you can say is we have a double, right? It's duplicated. That's the only thing you can say. It's duplicated. It's duplicated. Well, how about here? Well, here, you go here, and you know what? I think it's possible if we... So the odd numbered is fine. It's the even numbered that's an issue. So how do we do an even numbered? Let's see if we can use a counter. So it's going to be a counter. Yeah, I mean, be creative. Okay, visited is fine. I don't really care. We care about the temp, all right? So odd numbered is this, which is fine. Just current node in temp, done. Even numbered is going to be checked. So we don't check here. If odd is in temp, if node in temp, well, it depends. Well, for node in queue, for node, count C in queued items. Okay. If C is larger than 1, that is even number of nodes in cycle. Then we shall return 2 times the current level. Otherwise, we keep going. If node is in temp, odd number, then we can return here. Don't do this. Then this is going to be temp neighbor plus equal 1. Let's try. Okay. Yeah, I need to double check, see if this one works. This is early termination. Yeah, this we have early termination. This one works. Early termination. With 2 checks and a counter for each level. For even we'll put the same node in the next level. Thus, when we hit the next level, the problematic node will have more than one occurrences that the signal of an even numbered cycle. Alright, for odd numbered cycle, we'll notice that a node at the current level has been put into the next level. So now what? I think it's still O vertices times vertices plus edges. That's V. It's a V plus E. Yeah. Okay, let's see if this one works. Hopefully it does. Huh. Counter gets slower. But I can get out early. I guess it's... So this is actually solution... This is solution 2. Right, it's solution 2. Yeah, I want to copy the solution 1 as well. Solution 1 is faster. I think it's the counter's overhead is giving us trouble. Yeah, although we terminate early, I think the overhead of using counter is giving us a problem. But what if we don't use counter? What if we just use an array? Because the total number of nodes, right? That's 1000. Hold a second. What if we don't do counter? Each queue is going to be 0 times n plus 1 actually. Well, no, times n, and Q. Oh, then you don't know which one comes out. Yep, I think it's costing more. It's costing more time. Well, this solution does not terminate early, but it seems to be running faster. Does not terminate BFS early. I mean, it could be many reasons, so it doesn't really says anything. Okay, so that shall be it. I am not ending this yet because I still have to go through the discussion. I'm pretty sure there are better solutions. You see, somebody's right DFS, so you have to learn about that. Okay, that will be it for today. I will see you guys